Vapor and combined power cycles. Welcome to Thermodynamics 2. Today, we're diving into one of the most practical and impactful topics in thermal engineering, vapor and combined power cycles. This chapter isn't just about memorizing cycles, it's about understanding how we convert heat into work in real-world power plants. Whether it's a simple steam power plant or an advanced combined cycle that uses both gas and steam turbines, the principles you'll learn here are used every day to generate electricity around the world. Think of this as the point where theory meets reality, where the thermodynamic principles you've learned so far turn into turbines spinning and lights turning on. By the end of this session, you'll have a much clearer picture of how modern power systems operate and how efficiency improvements are achieved through clever cycle design. Let's get started and explore how engineers make the most of energy through these power cycles. Let's start with the basics of vapor and combined power cycles. These are the backbone of modern electricity generation, especially in power plants. The key idea here is simple. We use a working fluid that changes between vapor and liquid phases to convert heat into work. The Rankine cycle is the most common example. Think of it as the standard steam cycle used in most power plants. But to make these systems more efficient, engineers have come up with smart modifications. Methods like reheating the steam, regenerating heat within the system, and combining cycles together can squeeze out more useful work from the same amount of fuel. And there's something even more efficient: cogeneration. This approach doesn't just make electricity, but also captures leftover heat for other uses like heating buildings or running industrial processes. The result is a smarter, more efficient energy system where less energy goes to waste. Understanding these concepts will help you see how power plants evolve from simple systems into highly efficient energy producers. 2. The Carnot vapor cycle. Now, let's talk about the Carnot vapor cycle. On paper, the Carnot cycle is perfect. It's the most efficient cycle between two temperature limits, meaning it gets the maximum possible work out of a heat source. But here's the catch: it's not practical for real power plants. Why? First, the Carnot cycle requires isothermal heat transfer, meaning heat must be added or removed at a constant temperature. This is very hard to achieve when you're dealing with fluids that change phase, like water turning into steam. Second, the steam quality drops during expansion. This means more water droplets form in the steam, which can damage turbine blades, something we definitely want to avoid. Third, the cycle would require compressing a mixture of liquid and vapor, which is technically difficult and inefficient in practice. So while the Carnot cycle teaches us the upper limit of efficiency, in real life engineers use more practical cycles like the Rankine cycle that are easier to operate and maintain. 3. The Rankine cycle, ideal cycle for vapor power. Now we move to the Rankine cycle, which solves the problems of the Carnot cycle. It's the go-to ideal cycle for vapor power because it's much more practical to operate in power plants. The Rankine cycle is built on 4 simple processes. First, there's isentropic compression in a pump. This means we increase the pressure of the liquid without adding heat. Second, we have constant pressure heat addition in a boiler. This is where the liquid turns into high-pressure steam. Third comes isentropic expansion in a turbine. Steam expands, does work, and loses pressure. Lastly, we have constant pressure heat rejection in a condenser. Steam releases heat and turns back into liquid. To analyze the cycle's performance, we use energy equations to track the heat added and the work done. The key metric is thermal efficiency, calculated as net work output divided by heat input. This tells us how much of the input heat is effectively turned into useful work. The Rankine cycle shows us how to design a realistic, efficient power plant by focusing on achievable processes rather than theoretical perfection. Let's be realistic. Actual power cycles are never perfect. Even though we study the ideal Rankine cycle, real systems always have inefficiencies. One big reason is irreversibilities. These come from things like fluid friction and heat losses, which waste energy and make the cycle less efficient than the ideal model predicts. Another issue is pressure drops. As steam flows through pipes and heat exchangers, it loses pressure. This means the pump has to work harder to keep things moving, adding to energy consumption. Finally, turbines and pumps don't operate perfectly. Instead of being isentropic, they have mechanical losses, meaning the turbine produces less work and the pump consumes more energy than the ideal case. These real-world factors are why actual plants always have lower efficiency than the theoretical predictions. It's a reminder that in engineering, we always have to account for imperfections and design around them. 5. How to increase Rankine cycle efficiency. Now let's see how we can make the Rankine cycle more efficient. Remember, every improvement means more electricity from the same amount of fuel. The first method is lowering the condenser pressure. This reduces how much heat gets rejected at the end of the cycle, which means more of the heat is converted into useful work. Next is superheating the steam. By increasing the temperature of the steam before it enters the turbine, we raise the average heat input temperature. This improves efficiency because the cycle can extract more energy from the steam. Lastly, increasing the boiler pressure helps. Higher pressure raises the temperature at which heat is added. However, there's a trade-off. Doing this can increase the moisture content in the steam leaving the turbine, which can harm turbine blades if not managed properly. The key takeaway here is efficiency improvements often involve balancing trade-offs between performance gains and equipment limitations. 6. The ideal reheat Rankine cycle. Next, let's talk about the reheat Rankine cycle, a simple but powerful way to improve performance. The main goal here is to reduce the moisture content of the steam by the time it exits the turbine, which helps protect the turbine and boosts efficiency. The process is easy to follow. First, we expand the steam only partially in a high-pressure turbine. Then, before the steam gets too wet, we send it back to the boiler for reheating. After reheating, the now hotter steam is expanded again, this time fully, in a low-pressure turbine. This small modification of adding a reheater increases efficiency by around 4 to 5%. It's a smart way to get more work out of the same fuel while also making sure the steam stays dry enough to prevent turbine damage. 7. The ideal regenerative Rankine cycle. Let's look at another smart improvement, the regenerative Rankine cycle. This cycle focuses on using the heat we already have more effectively. The main idea is to extract some steam from the turbine before it completes expansion and use it to preheat the feedwater. This reduces the amount of heat we need to add in the boiler, which lowers fuel consumption. There are two ways to do this. The open feedwater heater directly mixes the extracted steam with the feedwater. Simple and effective. The closed feedwater heater keeps them separate using a heat exchanger, so steam transfers its heat without mixing with feedwater. By preheating the feedwater, we improve efficiency, reduce fuel use, and make the cycle more economical. It's a great example of how reusing waste energy can make a system smarter and greener. 8. Second law analysis of vapor power cycles. Let's go a step deeper and look at the second law analysis of vapor power cycles. This focuses on exergy, which is basically the maximum useful work we can get from a system. Unfortunately, not all energy is useful. Irreversibilities like friction, heat losses, and inefficiencies destroy exergy. That's why we use a second law efficiency, which compares the useful work output to the exergy input. It tells us how much of the potential work we're actually capturing in the system. Interestingly, the biggest exergy destruction happens during heat transfer to steam, especially in the boiler. This is where a lot of energy potential is lost because of temperature differences and inefficiencies in the heat exchange process. Second law analysis helps us pinpoint where losses happen, so engineers can focus on improving the weakest links in the cycle. 9. Cogeneration, power and heat production. Let's talk about cogeneration, an excellent way to boost energy utilization. Cogeneration uses steam for two purposes at once: generating electricity and providing process heating for industrial or building use. This approach eliminates waste heat, meaning we use more of the input energy, which improves overall efficiency. We measure this through the utilization factor, which combines both net power and useful process heat and divides it by the total heat input. Flexible cogeneration plants are even smarter. They can adjust how much steam goes to turbines or is extracted for heating based on what's needed more, heat or electricity. This adaptability makes cogeneration plants more efficient, cost-effective, and environmentally friendly. 10. Combined gas-vapor power cycles. Let's look at combined power cycles, which are a clever way to get more energy out of the same fuel. Combined cycles use two types of turbines: gas turbines following the Brayton cycle and steam turbines using the Rankine cycle. Here's how it works. Gas turbines run at very high temperatures and produce electricity, but their exhaust gases are still hot. Instead of wasting that heat, we capture it and use it to produce steam, which drives a steam turbine and generates even more electricity. This smart design achieves much higher overall efficiency, often above 50%, compared to using just one cycle alone. Combined cycles show how combining different technologies can dramatically improve performance and reduce waste in modern power plants. 11. Binary vapor cycles. Special topic. Let's end with a special topic: binary vapor cycles. These cycles use two different working fluids to boost efficiency. A common example is mercury and water. The high-temperature fluid, like mercury, runs in what's called the topping cycle. It extracts energy from high temperatures where it works efficiently. After that, the remaining heat is passed on to water, which runs in the bottoming cycle to capture the lower temperature energy. This setup gets closer to the Carnot cycle's ideal efficiency, but there's a catch. Using fluids like mercury comes with high costs and serious safety concerns due to toxicity, which limits its use in modern applications. Binary cycles show how combining different fluids can improve performance, but they also remind us that practical considerations like safety and cost always matter.